Imagine you're trying to teach a neural network to translate English into French. The problem seems straightforward until you realize something fundamental. The input sentence and the output sentence don't have the same length, they don't line up word for word, and the relationship between them is messy and non-monotonic. A French translation might reorder phrases, collapse 3 English words into one, or expand 1 English word into 5. Standard deep neural networks of the early 2010s could classify images or recognize phonemes beautifully, but they had a rigid requirement: fixed size inputs producing fixed size outputs. Sequences of unknown length broke the entire paradigm. This 2014 paper from Sutskever, Vinyals, and Lee at Google asked a deceptively simple question. Could you train a neural network, end-to-end, to map an arbitrary input sequence to an arbitrary output sequence without baking in any assumptions about how they align? The dominant approach at the time was statistical machine translation, often called phrase-based SMT, which worked by learning probabilistic mappings between chunks of source and target language using enormous hand-engineered pipelines with alignment models, language models, and reordering models stitched together. Neural networks had been creeping into these pipelines, but usually just as a rescoring component, taking the top 1,000 candidate translations produced by the SMT system and re-ranking them. A few researchers had begun trying to use neural networks for translation more directly. Kalkbrenner and Blunsum had mapped sentences to vectors using convolutional networks, but convolutions throw away word order. Cho and colleagues had used a recurrent neural network architecture similar in spirit to what this paper proposes, but mostly for rescoring, and they observed that performance degraded badly on long sentences. The intuition many researchers had was that compressing an entire sentence into a single fixed-size vector was simply too lossy to work at scale. The core idea in this paper is elegantly simple. Use one long short-term memory network, or LSTM, to read the input sentence one word at a time. After it consumes the final word and an end-of-sentence marker, its hidden state is a fixed-dimensional vector that supposedly encodes the meaning of the entire sentence. Then hand that vector to a second LSTM, which acts as a conditional language model. It generates the translation one word at a time, with each predicted word fed back in as input for the next step, until it produces its own end-of-sentence marker. The first LSTM is the encoder, the second is the decoder, and together they form what we now call a sequence-to-sequence architecture. The mathematical object they're modeling is the conditional probability of the output sequence given the input sequence, factored as a product of next word probabilities, each conditioned on the encoded source vector and the words generated so far. Why use LSTMs specifically rather than vanilla recurrent networks? Because vanilla RNNs struggle with long-range dependencies due to vanishing gradients during backpropagation through time. LSTMs solve this with a gating mechanism that lets information flow across many time steps without being washed out. And in this architecture, the gap between when the encoder sees a word and when the decoder needs to produce its translation can be enormous, so you need that long-range memory. Now here's where the paper gets clever and a little weird. The authors discovered that if you reverse the order of the words in the source sentence, but leave the target sentence in its natural order, performance improves dramatically. Test perplexity dropped from 5.8 to 4.7, and BLEU score, the standard translation quality metric, jumped from 25.9 to 30.6. Think about why this might work. If you feed in the English sentence ABC and want to produce the French alpha, beta, gamma, then in the normal ordering, A is separated from its translation alpha by the entire length of the input plus the start of the output. The optimizer has to learn a very long-range dependency to connect them. But if you reverse the input to CBA, then A sits right next to alpha in the unrolled computation graph. The first few words now have short paths to their translations. The authors describe this as reducing the minimal time lag of the problem. It's like rearranging a relay race so the first runner hands off to the first runner of the next team, instead of waiting until everyone has finished. The average distance between corresponding words is unchanged, but those crucial early connections that bootstrap the learning are now short. This trick, which sounds almost like a hack, turns out to be one of the key technical contributions of the paper. The actual model is substantial for its time. 4 stacked LSTM layers, each with 1,000 cells, 1,000-dimensional word embeddings, an input vocabulary of 160,000 English words, and an output vocabulary of 80,000 French words. The sentence representation that gets passed between encoder and decoder is 8,000 real numbers. Total parameters, 384 million. Training used stochastic gradient descent with a fixed then decayed learning rate, gradient clipping to handle occasional exploding gradients, and a nice engineering detail where they batch sentences of similar length together to avoid wasting computation on padding. Training ran on an 8 GPU machine, with each LSTM layer pinned to its own GPU, and the remaining 4 GPUs parallelizing the softmax over the large output vocabulary. Training took about 10 days. At inference time, they used beam search with a small beam, keeping the top few partial hypotheses at each step and extending them word by word until end of sentence. Remarkably, even a beam of size 2 captured most of the benefit. On the WMT'14 English-to-French task, an ensemble of 5 reversed LSTMs achieved a BLEU score of 34.81, beating the phrase-based SMT baseline at 3330. This was the first time a pure neural translation system outperformed a strong phrase-based system on a large-scale benchmark. And when they used the LSTM to rescore the 1,000 best candidates from the SMT baseline, they pushed BLEU to 36.5, within half a point of the best published result. Equally striking, the model handled long sentences gracefully, with essentially no degradation, up to 35 words, and only minor degradation beyond that, contradicting earlier pessimism about fixed vector bottlenecks. The authors also did a qualitative analysis showing that the learned sentence vectors clustered by meaning were sensitive to word order and were relatively invariant to active versus passive voice transformations, suggesting the model had learned something genuinely semantic. The limitations are worth noting honestly. The 80,000 word output vocabulary meant rare words got replaced with an unknown token, which penalized the BLEU score and capped the achievable quality. The fixed vector bottleneck, while it worked better than expected, would soon be recognized as a real limitation, and within a year, Bachtenau and colleagues would introduce attention mechanisms that let the decoder look back at every encoder state, eliminating the bottleneck entirely and setting the stage for the transformer architecture. The reversing trick, while effective, is a bit of a band-aid. Attention later made it unnecessary, and training took 10 days on 8 GPUs for a single model, with an ensemble of 5 required to hit the headline result. Now let's walk through some questions you might have after hearing all of this. Why did they use 2 separate LSTMs, one for encoding and one for decoding instead of a single shared network? The authors give a practical reason. It roughly doubles the parameter count at negligible computational cost, since at any moment only one LSTM is active. It also makes it natural to train the same encoder against multiple target languages, or vice versa, since the 2 halves can specialize for their respective languages and tasks. Conceptually, the encoder and decoder are doing very different jobs, one comprehending and one generating, so giving them separate weights lets each focus. Why does reversing the source sentence help so much, when in principle, the LSTM should be able to learn long-range dependencies anyway? The honest answer is that LSTMs can in theory learn long-range dependencies, but the optimization landscape matters enormously in practice. Gradient signal weakens as it propagates back through many time steps, even with LSTM gating. By placing the first few source words near their first few target words, you give the optimizer some easy wins early in training, and those early successes seem to bootstrap the rest of the alignment. It's a reminder that data ordering and problem framing can be as important as architecture for trainability. How does beam search actually help at decoding time? And why is a small beam enough? Greedy decoding picks the single most likely next word at each step, which can lead you down a path that looks good locally but becomes a dead end. Beam search keeps several partial hypotheses alive in parallel and extends all of them. So if one locally good choice leads to a bad continuation, another candidate can win out. The finding that beam size 2 captures most of the benefit suggests that the model's probability distribution is usually peaked enough that the top choice is right, but occasionally a runner-up needs the chance to prove itself. For large-scale recommendation systems, the ideas in this paper translate surprisingly directly. User behavior is fundamentally sequential, a stream of clicks, watches, purchases, or queries unfolding over time. The encoder-decoder formulation maps naturally onto problems like predicting the next sequence of items a user will engage with given their history, or generating a personalized session of recommendations conditioned on a query plus recent activity. Modern transformer-based recommenders like SASREC and BERT4REC are direct descendants of this line of work, and the core insight that you can compress a variable-length user history into a dense vector that captures intent is now standard practice for candidate retrieval, where you encode the user once and do approximate nearest neighbor search over an item embedding space. The practical lessons also carry over. The reversing trick is a specific instance of a general principle. How you frame and order your input data has enormous impact on what the model can learn, which matters when you're designing features like recency-weighted histories or hierarchical session representations. The engineering details around batching sequences of similar lengths, gradient clipping, and pipelining layers across accelerators are still relevant for training large recommender models at production scale. And the broader message that a relatively simple end-to-end neural approach can outperform a heavily engineered pipeline given enough data and compute, played out the same way in recommendations as it did in translation, with neural two-tower and sequence models gradually displacing older collaborative filtering and feature-engineered gradient boosting stacks at the largest platforms.